Hey everybody, Mr. Hayes back here with Hayes' World of Math. We're going through statistics right now, and we're going to wrap up and put a bow on the basics of doing a significance test. And we're going to do that through something that happened in Michigan that you may have heard of, the Flint water crisis. And again, I'd like to thank StatsMedic, and in this case, Skew the Script for putting this together. All of these notes you can find on the link down below. I also have a link to the data table that we'll be using for the randomness down below as well. While you're down there, if you like what you're seeing, like, comment, subscribe, and we'll go from there. What ended up happening back in 2014 is the city of Flint decided to switch their water supply from the city of Detroit to the Flint River. And as things continued, the people of Flint were starting to complain about the quality of their water. So what's going to end up happening, and the government said, hey, it's fine, don't worry about it. Okay, so what we're going to go through and we're going to do is we're going to simulate an investigation that outside researchers did, so we can kind of see how this works in the real world. Okay, so the setup here is we're going to try to, so here's the setup and the explanation of the stuff that was going on. So again, 2014, they swapped the water supplies. Starting in 2014 and into 2015, the residents start complaining about the water. And 2015, the mayor drinks the water on television to prove that the water is safe. And at that point, people came in to investigate what's going on. Now, as I said, if you can use a random number generator, here is a list of, I think it's 1,000 homes. 900 homes. Oh yeah, 1,000 homes. So you can see down through here, here's the home numbers, etc. So what each of the students would be doing is you're going to pick 5 random numbers from 1 to 1,000. And it's going to pick a different house here. And what will end up happening is that if you get a 0, that says there's a trace insignificant amount of lead. And if it's a number that's higher than that, then obviously there's an issue. So I went through and I did it. And so again, here you want at least 15 parts per billion. So I got a low, high, low, low, low. All right. Now, since we haven't done this, this is a new lesson from StatsMedic and Skew the Script. I haven't done this with my class, so I'm using their data. But again, it's pretty straightforward. So you're going to total up all of the high lead homes that happened in the simulation together. So you got 24. And then do the low lead homes, and that's 126. So there's a total of 150 pieces of data here. And then from there, our P statistic is going to end up being about 16%. Okay, so our P hat, 24 out of 150, 16% of our homes in Flint, according to the simulation. Now, obviously, the people in real life randomly picked the homes and tested the water there. And then, by the way, there is some 40,000 homes in the Flint area that went through and got tested for this. So then from there, according to EPA guidelines, if more than 10% homes in a city, not far enough, have lead content higher than the content, then what will end up happening there is that the whole city's water supply is deemed unsafe. So obviously we have some evidence, because 16% is bigger than 10%, that we're we're going in that direction. Okay. So now the question is, can we run a significance test to actually prove that we have evidence to say that? And so that's what's going on here. Okay, so the first thing that we need to do is that we're going to state what we're doing and what the important players are. So we're going to say here that P is the true proportion of Flint homes with high lead content. Our statistic here, P hat, is 24 out of 150. And again, the proportion is important, so they can kind of get a sense. And plus, it also helps drive home what your N value is equal to 16%. Our null hypothesis is that the water's fine. We're good. We're not over that level of 10%. So this is coming from here. Okay. And our alternative hypothesis is that the water is unsafe, that the proportion of homes in the city of Flint that have lead in their water is bigger than 10%. Now, if you start noticing a trend like this is very similar to what you're seeing, what we saw with confidence proportions or confidence intervals, it is. For proportions, it is. Okay, so it's going to be a very straightforward process. So remember, after we stated, we planned. So we name the procedure. We're doing a 1-sample z-test for proportions. So again, you're setting up the audience. This is what we're going to do. Check the conditions. So again, like we talked about yesterday, we need it to be random. we need the 10% rule to be met, and we need large counts. Randomness, we did a simple random sample. Okay. This over here, remember what this does, is that this allows us to generalize it to the population. If it wasn't random, we could only talk about the sample itself. And here, we don't want to test necessarily all 40,000 homes, though I'm sure the people of Flint would be fine with it. We don't need to test all 40,000 homes. We want to make sure that whatever we take can be generalized to all 40,000 homes. Over here, the 10% rule, 150 is definitely less than 10% of our 40,000 Flint homes. Okay, so that means that what this does is, again, remember, it's our independence. So sampling without replacement is okay. And then large counts. You need to have at least 10. You need to make sure that in order for this to work, okay, so that we can approximate this as normal, you need to have at least 10 instances in both the failure and the success categories. So in here, 10% of 150 is 15 is bigger than 10, and then 150 of 90, or 90% of 150 is going to be 135. So again, what this does is allows us to say P is approximately normal. P hat is approximately normal then. And I was saying to my stats class yesterday, the thing to remember about this is that this context right here allows you to kind of design this study right from the beginning in terms of how big your sample size has to be. So for example, if here with 10%, we need this to be at least 10, which means that I need a sample size of at least 100. Why? Because 10% of 100 is 10. Okay, so if you kind of know where your p-value is, you can kind of gauge how big of a sample you have. Obviously, you probably want to go a little bit further than that just to make sure that you've got everything. You know, can't be called into question, but that's something to keep in the back of your head. So we have state, we have plan. It's time to do this. Just like with confidence intervals, we're going to write down the general test statistics, or the general formula for a test statistic is that you're going to take the statistic minus the parameter divided by the standard deviation for that statistic. Our specific formula in this case, and if you copied my notes, I apologize. The formatting here got a little goofy when it got moved into a PDF. So you may need to readjust this a bit. Z is equal to P hat minus P divided by our standard deviation. Same as what we were doing yesterday. And our picture, and again, this is to help us get a sense of where we're going, what sides we're doing, things like that. So I've got 10% here. I've got 16% here. It also drives home that we're doing it as a normal curve, and I want to go bigger than 16%. So then we're going to go through and we're going to do our work. So I put in my work, the numbers here. And again, for a standard deviation, remember P hat and P can be, you can use, take it back. You can use P for your standard deviation here because the mean is going to be the same. And then over here for our test statistic, I get 2.45. So I'm going to rewrite that clearly over here that Z is 2.45. And then my value over here is going to be 0.07 as a probability. Okay. So then, and the other thing here, just in the back of your head, remember that as long as you get something bigger than 2, because again, we've got the empirical rule 68, 95, 95, or 99.7 rule. Once you hit 2 standard deviations, you've got 5% on both sides, right? Both tails total 5%. So that means that one tail is 2.5%. So then you know automatically that we're going to be underneath our alpha threshold of 5%. The other thing that that does is that saves some of this work here in terms of like, you know going in with that, where if you're just doing it with straight values, and that's more for means, it becomes more of an issue there. The other thing here too that you probably want to say, like, we did that via table A, or you put in your normal CDF there. Now for the conclusion, we talked about this yesterday. We're going to do the first part of what we talked about, and then we're going to wrap it all up. So first of all, we're going to interpret our p-value. Assuming that H naught is true, P is equal to 10%. There is a 0.007, or as some of us say, 007, probability of getting a sample proportion, a p-hat value of 0.16 or greater purely by chance. Okay, so this is interpreting our p-value. So you're explaining that what we're seeing here, if we assume if we take the assumption for face value, what we're seeing is this unlikely. So in this case, it's fairly unlikely, it's less than 1%. So then the conclusion is going to be over here, because 0.007 is less than 0.05, we reject the null hypothesis, and we do have convincing evidence that Flint's water is unsafe. So again, here is my conclusion. So you have to set up and explain why it's significant, and then wrap it all up so people don't have to worry about doing it for themselves. Okay? Now, taking this a step further, Virginia Tech study, and there's a link to it below. Yeah, okay. Randomly selected 252 homes in Flint. Of those, 42 had higher lead content, and they had a p-hat value of 17%. So compared to our class data, does the study give more or less convincing evidence for the water supply at Flint, and why? It's going to be more convincing evidence. 2 reasons. Most people are always like, hey, 17 is bigger than 16. It's more convincing evidence. Good, you're right. That's the first one. Their sample proportion p-hat is further from our null hypothesis value of 10%. The other thing to think about is this. Remember what happens when we did 150 households, they did 252. What happens when our sample size goes up? When our sample size goes up, the normal curve gets narrower. Our standard deviations come in. Why? Because here, they're going to be dividing by 242 instead of 150. So this bottom number that we're dividing by is going to get smaller, which is what's going to happen to our z-value then. It's going to spike up. And so because of that, the larger sample size also will help drive home that their evidence is more convincing than what we have. All right? So we're going to wrap all of this up in a nice big bow in video 2. If you have any questions, obviously, go ahead and link down below. Google this. This has been a hot button topic here in the Midwest for quite a while. And so hopefully, if a little bit more research, you can see how important statistics can be. Wow, that sounded really teacherish, didn't it? Anyway, we'll talk to you soon. Bye.